All right, last class we talked about naming type 1 and type 2 binary ionic compounds. And this class we're going to get into more than just binary compounds, but we're going to get into polyatomic ions, which when you break that word down means many atoms, right? And we are also going to talk about some covalent bonding. So let's jump right into polyatomic ions. This is an ionic compound with a polyatomic ion, like a compound like ammonium nitrate, which is NH4NO3, and it contains two polyatomic ions. So more than just two separate ions, two distinct ions, we have two polyatomic ions. Now, we still would break this down into two parts. We still have this positive part and this negative part, but in this case, they are polyatomic, many atoms, rather than just single atoms. So, as you can see, that NH4, that ammonium, has a positive charge and nitrate has a negative charge. Now, these are going to just be basically taken from this table right here with all these special names. We won't spend a lot of time on how they got their names or how to name them from the polyatomic ion. It's just basically if you see any of these groupings right here on any of your ions or on any of your compounds that you're trying to name, then you should know that it's a polyatomic ion. Or if you see something with like four atoms, different types of atoms in it, or three different types of atoms, you should suspect that it might be a polyatomic ion. Okay, this is a list of them. This is also in your textbook, I think on page 65, so you can observe that. I do not require that you memorize these, so don't worry about that. Okay. Some anions contain an atom and a given number of oxygen atoms. So this is basically the rule for these anions. They are called oxyanions because they contain oxygen in them, and they have different numbers of oxygen. When there's a series of a specific atom and oxygen atoms that has only two variations, the smaller number ends in ite and the larger number ends in ate. So if it's O2 and O3, that number of oxygens, the O2 would end in ite and the O3 would end in ate. So you can see that with the examples of sulfite, SO3, and sulfate, SO4, because 3 has fewer than 4, so that's the ite versus the 4-8. Okay, when a series of specific atom and oxygen atoms contain more than two variations, which would be you'll see some examples. The lowest gets hypo and ite, and the highest gets per and ate. Okay, so we get that ite ending in between and the ate ending in between, but then we have more of them. So here's an example, hypochlorite, right? So that hypo prefix right here, which means hypo means less than. So think about like hypothermic. You are under temperature if you are hypothermic, right? So hypochlorite means it has fewer oxygens and it has this ite ending. Now, for the second one in this series, it's just ite, so we still obey that rule. Third one is ate. So think about these in terms of, this is like the fewer of the middle, this is the more greater of the middle. And then finally we get another prefix, per, which means more, and ate, ate. So you can see those right there. Both of the oxygens with the fewer number contain ite, both of them with the greater number contain ate. Here's a little bit of naming practice. Now we still have to name the cation like we did before. We will look at the periodic table. We have sodium, which we recognize to be in group 1. So it has a positive 1 charge for each sodium atom, right? Total, it would have a charge of positive 2 for the net charge on just sodiums, right? But now we also need to look at the negative polyatomic ion. Also, we don't need to be too concerned about that sodium because the charge of the sodium, because it doesn't change how we name the cation, right? Now the negative polyatomic ion, we have to double check the amount in the series and its charge just for our information as well. It's the anion, it's SO4, and when we check the series, it has more oxygens than the others, so we would name it sulfate. So the final name is sodium, which is just the name for Na on the periodic table, and sulfate, right? So we should see, if we see multiple atoms, we should recognize, oh, that's a polyatomic ion, right? Here's another one. Now we have multiple atoms. We've got 4 different types of atoms. This one's interesting because you might think, oh, well, it's probably 2 and 2. But if you look at that list, we don't have any KH2 polyatomic ion. However, when you look at that list, you will see not this breakup, but you will see an H2PO4 as a polyatomic. That's why it's not just like biatomic or something or diatomic. We say polyatomic because it could be 2 ions, or it could be 2 atoms in that ion. It could be 3 atoms in that ion, or types of atoms rather. So it just needs to be polyatomic. Now, our positive ion then we recognize as potassium, which is in group 1 also. We know that that has a positive 1 charge. Then the negative polyatomic ion is that H2PO4, which we can see the charge from that table is -1. So we would call that potassium dihydrogen phosphate. Now, this is one of the only times that when we're naming ionic compounds, you'll see that di in the naming. We typically don't use prefixes except for these kind of odd special cases of the polyatomic ions. So just recognize that. Save those mostly for when we're doing covalent compounds, okay? Here's one more. When you have them grouped together like this, that is an even easier way to see a polyatomic ion, but what this is referring to is that NO3 is the polyatomic ion. This little sub 3 here is saying we actually have 3 of those NO3 polyatomic ions, okay? And in this case, this is actually more like a, like a type 2, where we have iron, this Fe, which is a transition metal, right? So we don't actually know for sure and certainly what iron's charge is, not every time that we see it. So we have to actually use our anion or our polyatomic anion to determine what the charge of iron will be, that transition metal. So this time we're going to look at the negative polyatomic ion first, the number of the amount in the series of oxyanions, right? And then we'll double check its charge. So we note that it is an anion. It has a total charge of -3 when we're looking at that. Then we can use that -3 charge to determine our cation's charge, right? If it's -3 here, we need an equal and opposite charge, as kind of we talked about last class as well, equal and opposite charge to have a neutral compound. And when we look at that, iron has to have a charge of +3, equal and opposite of the -3 from the anion. So we'll see that the name is iron 3 nitrate. Now, this thing that I've circled here is the actual name of the entire compound from up here. This nitrate is just to determine from the number in the series, that's kind of where we get that nitrate. But iron 3 nitrate is the actual official name. I do just want to note that similar thing here as well. Potassium dihydrogen phosphate, that's the name. This is just to get us that polyatomic ion. Same up here. Polyatomic ion, here's the name of the compound that we're actually looking for. So that's the final answer that you'll be giving like on your homework or on a test or a quiz or anything like that, okay? Now, what if we go the other way? Now we have sodium hydrogen carbonate. So here we've got to see the positive ion. That is sodium, which is in group 1. So we know that we already know the charge that it has a tendency to create, which is +1. Then we can look at the negative polyatomic ion and its charge, which hydrogen carbonate is HCO3 from that table. And it has a total charge of -1. So these combine in a ratio of 1 to 1. Just like that. Okay. Now remember, you You don't need to put this in parentheses like this one up here was. The only time you'll need to put that in parentheses is when you need another subtext to say, oh, there are 3 of these. But in this case, we don't because it's just a 1-to-1 ratio. Here's some continued practice we can do on our own. For this first one, I'll look at this with you, and because that has a transition metal, manganese, right? So manganese we see is on the periodic table. It is a transition metal, so we don't know which charge, or it doesn't really have a tendency to create a specific charge. So we have to look at our anion, which is hydroxide, OH, and it has a -1 charge. So I know that this has 2 of those, though, because of that little subtext 2, right? So I'm going to acknowledge that, which means that has a charge of -2 total, meaning our manganese must have a charge of equal and opposite value, +2. So we'll say manganese, and because it's a transition metal, we represent that charge with Roman numerals, and hydroxide. Okay? Now we've got cesium perchlorate. Cesium here, let's find that on the periodic table. That is also in group 1, so it's going to have a +1 charge. Now perchlorate I have to find in our table, which looking at it, it is ClO4 and it has a charge ClO4. Notice it's C lowercase l and then capital O4, and it has a charge of just -1. So when we put all this together, we can go ahead and say they're going to combine in a 1-to-1 ratio. So cesium perchlorate, ClO4. Okay, and since it's 1-to-1, we don't need parentheses around the polyatomic ion. We can just leave it as it is. I would like for you, before or on your homework, I would like for these to be questions that you start off your homework with, okay? So when you're done with this, I want you to try some more of those. All right, now we're going to look and change gears, and even you could have paused as well and looked back at this if you'd like. But right now we're going to practice those, because now we're going to change gears into binary covalent compounds. So remember, we've been dealing with ionic, which ionic is nonmetal bonding with metal, or rather metal bonding with nonmetal. And now we're going to look at covalent, which is nonmetal atoms bonding with nonmetal atoms. Binary covalent is just binary 2, right? We discussed that in class as well. Binary means 2. And we're dealing with nonmetals, so on the periodic table, that's on the right-hand side of things. Okay, so these binary covalent compounds should all be on the right-hand side. They don't contain ions. So we have some different rules. You can go ahead and write these down as well. The first element in the formula is named first, using the entire element's name. So if it's CO2, C comes first, that's the one that we're going to name first. And we use the whole name, like carbon, okay? The second element is named as if it were an ion. So in that CO2 example, it would be an IDE ending. So we would say oxide. But prefixes will be used to denote the number of atoms present. Now that's in both the primary element, the first element, and the second element. Okay, so we will use prefixes when necessary. So for example, that CO2, that O2, we need to include a prefix for 2, okay, for di. Now, the prefix mono is used, but only for the second element, meaning it will never be used for the first element. So when it says carbon, if it's CO2, there's only one carbon atom. When we say that, we don't need to say monocarbon. We can just say carbon. Okay, we only will use that mono in the second element if there is a single atom for that. Okay, here's an example of that. CO, not CO2, is carbon monoxide, not monocarbon monoxide. Okay, so you do not need that mono there. You can just call it carbon monoxide. Okay, here is a list of those prefixes right there. So when we are dealing with those, we could look at a compound, a covalent compound like N2O3. N2, we'll name that N first, so it's going to be nitrogen, but because of this subtext 2, we need a prefix of di, right? So we'll say dinitrogen, and then there are 3 oxygens, so we're going to use the prefix tri, and we're going to use the anion ending like we used it before in ionic bonding, but even though it's not an ion. So we'll say oxide, and the prefix will be tri, just like that, dinitrogen trioxide. Okay, here's another one. N2O4, we still have that 2 N's at the beginning, but now we have 4 oxygen atoms, so it's still dinitrogen, but instead of tri, it's going to be tetra, which this is a little interesting. We often think about 4 as quad, like quadrupedal or something like that. Something walks on 4 legs, or even like we call ATVs quads a lot of times because they have 4 wheels. But in chemistry, when we're naming these covalent compounds, instead of quad, we use tetra. Okay, so just keep that in mind as well. So we've got dinitrogen tetroxide. Notice that on that one as well, we dropped the A and used the O of oxygen. So it's not going to be tetraoxide, it's just tetroxide. And 205, we keep going. This time we get to use dinitrogen pentoxide. Okay, again, that A drops for the O. All right, here are some examples of covalent compound practice. Let's try that first one. The first one is phosphorus with 5 chlorine atoms. So we're going to say phosphorus. We don't need to include mono. And then 5 chloride atoms, or chlorine atoms, we'll say pentachloride with that IDE ending. So it's not pentachlorine, it's pentachloride. Here are some other ones. Sulfur hexafluoride, which we can see sulfur has nothing in front of it, which means there's 1. And then hexafluoride, we're going to have 6 fluorine atoms. So again, these will need to be on your homework practice. Here's a nice little table you can look at to determine if it's binary or if there are polyatomic ions present. If it is regular binary ionic, same rules, or if it's something totally different, we won't really consider this, so don't worry too much about that. Here's another one that's kind of helpful for general binary compounds. If there's a metal, then we can go through here and say, okay, what kind of polyatomic ions do we have, if possible? Or, sorry, what kind of ions could be formed? Is it a transition metal, or is it a regular non-transition metal? Here, we look at just using prefixes. And finally, we have acids, which are defined as a molecule that produces a solution containing free H plus or hydrogen ions, which are basically just protons because hydrogen atoms have 1 proton and 1 electron in their neutral state. But when you get rid of that 1 electron, you just have a proton. So an acid is also known as a proton donor. Some of the naming rules here are if the anion does not contain oxygen, we add the prefix hydro and suffix ic and add acid to the end. That's when it doesn't contain oxygen. If it does contain oxygen, then we check its order in the series of polyatomic ions, just like we did before. And if the suffix is ite, in that list of polyatomic ions, the series of polyatomic ions, then we change it to us so that we can denote that as an acid. If it is ate, then we change the suffix to ic. Okay, so what we're looking at is, does the anion, the negative polyatomic ion, contain oxygen? If no, then it's hydro, the anion root, end it with ic. So hydro something ic, acid, right? If it does contain oxygen, then we need to check the ending to see if it was ite or ate. If it's ite, we change the ending to us, O-U-S. If it's ate, then we change the ending to ic, and we include acid afterwards. So some examples would be HCl. Note there's no oxygen, so we call it hydrochloric acid. Okay, the ate goes to ic. In this one, we see oxygen, is contained in this anion. So we look at it in the series, it is a sulfate, so we would change that 8 to ic. Now we also have phosphate here. You can look at it in the series, that 8 changes to ic. Notice this one is a little bit different with phosphorus. We call it phosphoric acid now. Instead of phosphate, it is phosphoric acid. Okay. Then we've got this one where our anion is acetate. So it's another one of these that has more than just 2 types of atoms in the anion. And because of that ate ending, we change the ending to ic. So it's acetic acid. Okay. Now to look at some ite to OUS, we've got SO3, which when we examine it in this series is a sulfite ion. So we change it to sulfurous acid. So sulfurous acid. Then NHNO2, again, it's in the oxygen series, so we look at that. It's a nitrite ion, so we change it to nitrous acid because of that H. Here are some common names of these different types of acids as well. All right, go ahead and work on your homework. The substitute will write this on the board, but it is also, let me write it back here. It is questions 75 through 79. And 83. And don't forget to do those practice problems that I had circled earlier. All right, go for it.